When you think about solar power, your mind probably jumps to rooftops covered in shiny blue panels, right? But what if we thought bigger? I mean, civilization scale bigger. Today, we're going to look at a totally different, kind of radical approach to renewable energy, one that doesn't use a single silicon cell. We're talking about solar updraft towers. And look, that's not just hyperbole. The whole idea is to build a structure so enormous that it literally generates its own tiny, predictable weather system, a constant, powerful wind, and then just harvests the energy from it. This isn't just engineering, it's almost like applied meteorology. That's the billion-dollar question, isn't it? It sounds like something straight out of science fiction, but the physics behind it all is actually surprisingly simple. It all just comes down to trapping a whole lot of heat and then giving it only one way to escape, straight up. Okay, so let's dive into how this machine actually works. To really get it, we just need to break it down into its three core pieces. And forget about complex moving parts. The real engine here is nothing more than hot air doing what it naturally wants to do. It's really just a three-step process. First, you collect the sun's energy. Second, you funnel all that heated air into a powerful rising column. And third, you use that man-made wind to spin some turbines. Simple as that. Let's take a look at each part. So, the whole thing starts with the collector. I want you to picture a gigantic, circular greenhouse roof, maybe kilometers wide, just sitting a few meters above the desert floor. Sunlight just pours through it all day long, baking the ground underneath to, say, 70 or 80 degrees Celsius. Now, here is the secret weapon, the real genius of the solar updraft tower, the ground itself. It becomes this massive, completely free thermal battery. It soaks up all that heat during the day and just keeps on radiating it back out, long, long after the sun has gone down. And what does that get you? 24/7 power. That's the big one. Unlike your standard solar panels that just go to sleep at sunset, this system just keeps on chugging along, heating the air and making electricity right through the night. That is the holy grail for renewables: consistent, reliable power without needing a mountain of expensive batteries. Okay, so you've got all of this superheated air trapped under the collector. It's way less dense than the air above it, and it desperately wants to rise. Well, sitting right in the middle of this giant greenhouse is the chimney, a colossal tube that provides the one and only exit. It basically turns into a giant vacuum cleaner for hot air. Now imagine all that hot air from this vast collector suddenly getting funneled into the narrow base of the chimney. It accelerates like you wouldn't believe. We're talking about creating steady, hurricane-force winds. And right there at the base, you place a ring of turbines specially designed for this kind of airflow. They just sit in that path, capturing all that kinetic energy and converting it into electricity. But, and this is a huge but, for any of this to work economically, there's a catch, and it's a big one. The whole system is governed by this fundamental law of physics that demands one thing above absolutely everything else: size. The entire machine is powered by something called the stack effect. It's honestly the exact same reason a fireplace chimney works. Hot air is less dense, so it rises. The bigger the difference in temperature and density between the hot air at the bottom and the colder air at the top, the stronger the draft. So here's the absolute rule of the game for these things. Height is everything. The taller the chimney, the bigger that pressure and temperature differences between the bottom and the top. This just supercharges the stack effect. So doubling the chimney's height doesn't just double the power. Oh no, it increases it exponentially. It creates a far, far more powerful updraft. To really wrap your head around that kind of scale, just look at this. The chart here shows the very first prototype next to the Burj Khalifa, the tallest building in the world. A commercially viable solar updraft tower would need to be even taller than that, stretching a full kilometer up into the sky. A structure like this is a massive engineering challenge. It pushes the absolute limits of material science. Now, you might be thinking, this is all just wild theory on a whiteboard, right? Well, it's not. A prototype was actually built, and it ran for years, giving us some incredibly valuable real-world data on how these sun engines actually perform. So back in the 1980s, a German-funded project down in Manzanares, Spain, built a tower that was 195 meters tall. It only produced about 50 kilowatts of power, enough for maybe a few dozen homes. But from a scientific point of view, it was a monumental success. It ran for 8 years, it proved the physics were totally sound, it generated power at night, and it needed almost zero maintenance.
But at the same time, Manzanera has taught us that very hard lesson about scale. At that size, the power output just wasn't enough to make any economic sense. The entire business model for these things hinges on going gigantic to bring that cost per megawatt down. You have to push the design to the absolute limits of engineering.
So let's say we do it. We overcome the engineering challenges and we figure out how to build these things at this immense scale. What does the future of this technology actually look like? What else can it do for us besides just generating power? And this is where the idea gets even cooler. That giant collector at the base, it's not just a heater, it's also a massive greenhouse. You could actually grow high-value crops under it, a practice people are starting to call agrovoltaics, creating a whole second income stream. That constant warm airflow is also perfect for powering desalination plants, creating fresh water from seawater. For countries in arid regions, this could be a ticket to both energy and water independence, turning their most useless land into their most valuable asset.
And that kind of leaves us with one last, pretty powerful thought. We tend to look at the great deserts of the world, the Sahara, the Australian outback, and we just see barren wasteland. But with technology like this, they could be transformed into the most productive and reliable clean energy sources on the entire planet. So the real question is, are we ready to think that big?